oil, natural gas, solar, wind, and hydroelectricity. These are all examples of energy sources we use around the world today. However, there's been a relatively new development going on, known as fusion energy, in which several countries around the world are currently researching. Just to give you an idea of how much has already been invested, the Fusion Industry Association says that around $6 billion have already been invested. This new form of energy seeks to power our civilization the same way the sun powers itself. Instead of splitting atoms apart like in nuclear fission, it seeks to join them together to release more energy than in nuclear reactor. And the best thing about it is that it can be powered by an isotope found in abundance in seawater. Hello, and welcome to That One STEM podcast. I'm your host, Vihan, and today we'll be looking at a revolutionary new method to generate tremendous amounts of energy, and that method is known as fusion energy. We'll be talking about its inner workings, how it can be powered by certain materials found in seawater, and how it can help us beyond just giving us unlimited power. So, how does this new method of energy production even work? Well, it uses a process known as nuclear fusion to make energy. One of the best examples of fusion is our sun. It's easy to think that the sun is a big ball of fire. However, it's not. In fact, it's a giant ball of superheated plasma, which is a mixture of freely floating protons and electrons. Because of how big our star is, there's a lot of pressure on the core. And since the core is a mixture of plasma and it's under intense pressure, it'll fuse hydrogen atoms together to create massive amounts of energy to keep the star alive. Now, while we can't fully simulate the inside of a star, there are a few principles we can use to make a fusion reactor. Quoting from the International Atomic Energy Agency, in fusion reactors, light atomic nuclei are compressed under intense pressure and heat to form heavier ones and then release energy in the process. The process must be optimized to generate more energy than it consumes. Based on this information, we can derive three things. Firstly, the fuel must be made of light atomic elements such as deuterium and tritium, which are isotopes of hydrogen which have 1 and 2 additional neutrons respectively, compared to hydrogen which has none. Because of their atomic makeup, both isotopes are the ideal fuels for fusion reactors. Just to give you an idea of how much energy is released during the fusion process, the World Nuclear Association says that en masse, the fusion reaction releases 4 times more energy than uranium fission. Now, this is insane because uranium is one of the most energy-dense elements. According to the World Nuclear Association, deuterium, which is one of the fuel sources for fusion reactors, occurs naturally in seawater and therefore is in high abundance. However, tritium, the other fuel source, occurs naturally by cosmic rays, and if then only in trace amounts, which is why tritium must be made artificially in nuclear reactors or using lithium fusion processes. Secondly, there needs to be an intense pressure and heat for a fusion reaction to occur. This can be done by a variety of methods, which each their own respective type of fusion reactor. One of these reactor designs uses magnetic fields to manipulate the plasma by using superconducting coils in a method known as magnetic confinement, which typically uses a deuterium and tritium combination for the fuel. In case you're wondering, plasma is susceptible to being influenced by magnetic fields because of its electric charge. If you understand what electromagnetism is, then basically plasma can be controlled by magnets because of this fact. Another method is known as inertial confinement. According to the World Nuclear Association, this process uses a small pellet around a few millimeters in diameter, which contains the deuterium-tritium fuel. Then lasers or ion beams are focused onto the pellet. This heats up the outer layer of the pellet, which causes it to explode. The explosion then causes the core to implode and pressurizes the fuel up to 1,000 times its liquid density. Because of the heat and significant pressure, fusion occurs, and tremendous amounts of energy are released all at once and causes the rest of the fuel in the reactor to begin fusing. The crazy thing about this is that the reactions often occur in less than a millisecond. The third method is an interesting combination of both methods, using lasers to rapidly heat up the fuel for fusion and using a magnetic field to control the plasma. This method is known as magneto-inertial fusion, and the benefit of this method is that the plasma can be controlled for shorter times compared to magnetic confinements because it's using the heating systems from inertial confinement methods to make the plasma heat up faster. The compression from the plasma can also be achieved in longer timescales compared to those found in inertial confinement methods because of the use of magnetic confinement strategies. In summary, this method uses the best of both worlds. Now, there's a fourth method which uses fusion and fission reactors simultaneously to generate more energy, and the basis of this method is by using a fusion reactor as a source for neutrons for a fission reactor. Not too interesting, so we'll continue. Now, let's move on to the benefits of this technology and the other ways fusion can help us other than just providing energy. According to the International Atomic Energy Agency, here are the following reasons why fusion would be the ideal energy source. First, this method of energy production is eco-friendly as it produces no emissions and there is no long-lived radioactive waste produced. Another major benefit is that the major fuel source for fusion, deuterium, is widely available in our oceans, which cover most of the Earth's surface. Fusion is also very safe since fusion requires very precise conditions to occur. If a breach happens, then the fusion stops immediately, resulting in no harm done. Now, this sounds amazing. Fusion is an eco-friendly source of energy that can produce more power than nuclear energy and uses a widely available fuel. It's as if we found an energy cheat code, but it gets better than that. For example, fusion reactors can be used to power rocket propulsion systems. According to a paper from 2017 titled Inertial Electrostatic Confinement, Innovation for Electric Propulsion and Plasma Systems, fusion reactors can be used to improve electric propulsion systems by aiding in a rocket engine's accelerations of ions to improve efficiency. Another thing is that fusion energy can help in providing medical isotopes. In case you didn't know what a medical isotope is, it's used to diagnose and treat medical conditions such as cancer and heart disease. Due to their importance in treatment, we often must pay a lot of money for their creation. According to a paper in the journal Fusion Science and Technology, current methods to create medical isotopes use particle accelerators or nuclear reactors to produce medical isotopes. However, they can cost around 2 to 3 million. And the reactors and accelerators tend to be closer towards densely populated areas. Now, while this poses little health risk, it makes it difficult for remote areas to access these life-saving materials. However, according to the paper, IEC reactors or inertial electrostatic confinement reactors are small enough to be put on vehicles such as trucks and allow for easy transportation to remote areas. Also, their manufacturing cost would be significantly lower in the ranges of around 100,000 compared to the cost of 2 to 3 million for standard methods. Now, don't get me wrong, this is great news for our medical, space tech, and energy sectors and our daily lives. However, we're not quite there yet technologically to see these changes happen. Governments and businesses are investing millions into developing this technology, and while we have reactors, there are several issues we need to overcome. One of the many is cost. For example, the International Thermonuclear Experimental Reactor, a fusion reactor that will be built by a collaboration between 35 countries, is insanely expensive. According to a news article by the Scientific American, the construction could cost an estimated $22 billion compared to the starting budget of around $6.3 billion. So clearly we have some way to go before we can make these reactors affordable enough. However, we shouldn't lose hope for the future. Fusion energy has shown that it can break the break-even point, or the point where it generates more energy than the energy needed to power the reactor. According to an article on the U.S. Department of Energy's website, the National Ignition Facility, or NIF, has breached this point in 2022. Just to show you how much was produced, 2.05 megajoules of energy were used to power the lasers which started the reaction, and the fusion reaction produced 3.15 megajoules of energy. In percentages, that's around 154% according to my calculator. In the end, this technology will have a massive impact on our lives with plenty of energy, improved spaceflight, cheaper medical isotope creation, and other things that I didn't have to mention. However, we need to be sure that we use technologies like these responsibly. Thank you for listening to this week's episode. If you liked it, feel free to follow us on whatever platform you're currently listening on. And you can email us at thatonestempodcast@outlook.com. In case you're wondering, our sources are in the description. I wish you a great week and keep on learning.